To kick things off, let's first ask the most basic question. What is a vector? It's hard to talk about whether a single object is a vector or not. Instead, we talk about a collection of objects called a vector space, and the objects in the vector space are called vectors. So what is a vector? It's an object in a vector space. Great. So what is a vector space? Well, to talk about a vector space, we need four things. First, we need a set called V. These are going to be our vectors. Then we need a field. I'm not going to go into the definition of what a field is, but we're going to call these scalars. And for now, just think of these as being the real numbers or complex numbers. We need a way to add vectors together to get another vector. So if I add two vectors, I get another vector. I need a way to multiply a scalar by a vector, and it needs to result in another vector. So given these, I can say that V is a vector space over F if the following 8 properties hold. So the first two are properties about how addition of vectors is defined. So the way we define vector addition needs to be commutative, meaning that the order of the addition does not matter. And it needs to be associative, meaning that if I want to add 3 vectors together, it doesn't matter which 2 I add first. Then I need to have an object in V that basically acts like 0. If I add it to anything, I get that same thing back. So adding this 0 vector doesn't do anything. They call this the additive identity because when I add it, I get identically the same thing back. Then I need to have that the negative of a vector is in V as well. And the negative of a vector is defined by being the special thing that when I add it to x, I get the 0 vector. So if I take x and I add the negative of x, it gives me the 0 vector. So these 4 properties right here, these are all special because together they tell us that a vector space is what in abstract algebra is called an abelian group. The next 3 are all properties about how scalar multiplication works with addition. Most importantly, that we can distribute down here. Note that if I was to change how I defined vector addition, then the additive identity, the 0 vector, would probably look different. Similarly, if I change the definition of addition, the negative of a vector, the additive inverse, would probably be different as well. If I was to change V, the field that I'm using, the definition of addition or the definition of scalar multiplication, it's going to give me a different vector space. If I want to show that something is a vector space, I need to show all 8 of these properties. But if I'm told in advance that a set is a vector space, then I can assume that all 8 of these properties hold. So let's see some examples on how I can use these properties to do some basic algebra. Let V be a vector space over F, so V are the vectors and F are the scalars. Show that if V plus W is equal to V, then W is equal to the 0 vector. So we want to show that if this is true, then this is true. So I'm going to assume that V plus W equals V, and then I'm going to use the definition of a vector space to then conclude that if we assume that V plus W equals V is true, then W is equal to the 0 vector. So first, let's assume that V plus W is equal to V. Then using property 4, we know that negative V exists. So let's add it to both sides. So we have minus V plus V plus W. is equal to minus v plus v. Now, let's use the fact that vector addition is associative. So using this on the left-hand side, we have that minus v plus v plus w equals minus v plus v. And now I'm going to use the fact that plus is commutative. So this gives me that v plus negative v plus w is equal to v plus negative v. Now I'm going to use the definition of the additive inverse. This gives me that this is going to be the zero vector plus w is equal to the zero vector. Right, and that's just the definition of the additive inverse. And now let me just use the definition of the zero vector because I have the zero vector plus w, and this gives me w equals the zero vector. So this lets me conclude that if v plus w is equal to v, then w is equal to the zero vector. Okay, so let's do another one. Let v be a vector space over F. Show that if v plus w equals the zero vector, then v is equal to the additive inverse of w. So again, we have an if-then. So we start off by assuming the part on the left, and we want to end up with the part on the right. So we assume v plus w is equal to the zero vector. And then I know that there's a special vector called the additive inverse, and I'm going to add it to both sides. So I'm just going to add the negative of w to both sides. All right, now I use the fact that vector addition is associative, so I have v plus w plus minus w is equal to zero vector plus minus w. This is by 2, the fact that it's associative. Now I use the definition of the additive inverse right here. So I have v plus the zero vector is equal to the zero vector plus minus w. And that is by 4, right? Because that's the definition of the additive inverse. And now we use the definition of the zero vector, meaning that if I add v to the zero vector, I just get v. And this is equal to, if I add 0 to negative w, I just get negative w. And there we go. So this is by 3. So this proves that therefore, if v plus w is equal to the zero vector, then v is equal to negative w. Thanks for watching. Be sure to subscribe if you want to see more matrix stuff.